Good morning and welcome to the lecture number 5 of the course Water Resource Systems, Modeling Techniques and Analysis. Now, we are discussing the unconstrained optimization problems, and in the previous lecture we discussed problems of single variables as well as problems functions of multiple variables. So, if you recall, for the single variables, the necessary condition for a function f of x to have an optimum at a point x is equal to x naught is that the slope of the function at that point x is equal to x naught must be 0. That is, f dash of x, the first derivative of the function with respect to the variable, must be 0 at that particular point. So, to examine whether a function f of x has optimum at a given point, first you have to check whether the slope is 0 at that point. But typically what we do is that given a function f of x, we get the first derivative f dash of x, equate it to 0 and then obtain all the solutions corresponding to f dash of x is equal to 0. These solutions are called as stationary points. At each of the stationary points, then we will examine whether the function has a maximum or a minimum or neither of them. So, we use the sufficiency conditions. We go to the higher order derivatives, second order derivative, third order derivative, fourth order and so on, and capture the first non-zero derivative and look at the sign of that non-zero derivative. If the order at which the first non-zero derivative is odd, then the function has neither a minimum nor a maximum at the particular stationary point at which the derivative has been determined. If the order of the first non-zero derivative is even and the sign of this derivative at that particular stationary point is negative, then the stationary point corresponds to a maximum value of the function. If the sign is positive, then the stationary point corresponds to a minimum value of the function. So, this is what we saw in the previous lecture. We have written here for the second derivative, that is f dash of x is equal to 0 and the sufficiency condition is f double dash of x evaluated at x naught. X naught is the stationary point that comes from here. If it is less than 0, then it corresponds to maximum. If it is greater than 0, it corresponds to minimum. And recall that if the second order derivative is 0, then you go to the higher order derivatives and capture the first non-zero derivative and so on, then look at the order of the derivative. If it is odd, then the particular stationary point x naught corresponds neither to a minimum nor to a maximum. If it is even and the sign of that particular derivative is negative, then it corresponds to a maximum. If the sign is positive, then it corresponds to a minimum. Then we went on to extend this for functions of multiple variables x1, x2, x3 etc. You have n number of variables. So, f is a function of n number of variables. Then the necessary condition is that the first derivative of the function with respect to each of these variables must be equal to 0. And then for the sufficiency condition, we looked at the Hessian matrix, formulated the Hessian matrix, which is in fact a matrix consisting of the second order derivatives of the function d square f by dx1 square, d square f by dx1 dx2 and so on. This is for two variables is what I have seen, what I have shown here, but typically it will be a n by n matrix. We look at the Hessian matrix and then if the Hessian matrix is positive definite, then the particular point, this Hessian matrix is again evaluated at the stationary point. The stationary point is obtained by solving these equations, n number of equations, you obtain solutions for the n number of variables, they constitute the stationary points. At the stationary point, you evaluate the Hessian matrix. At the stationary point, if the Hessian matrix is positive definite, the particular stationary point corresponds to a minimum. If at that particular stationary point, the Hessian matrix is negative definite, then the stationary point corresponds to a maximum value. we have also seen what is a positive definite matrix, what is a negative definite matrix. If all the eigenvalues of the Hessian matrix are positive, then the Hessian matrix is positive definite. If all the eigenvalues are negative, then it is a negative definite matrix. So, we will continue with the examples of multiple variables. We are still in the domain of unconstrained optimization. Remember, we are talking about unconstrained optimization, where we are looking at the optimum values of the functions without attaching any constraints to that. So, we will now see some more examples of functions of multiple variables to examine different cases that are possible for stationary points, for the optimal solutions, for global minimum, global maximum, and so on. So, we look at function minus x 1 square minus x 2 square minus 4 x 1 minus 8. So, this is a function. We will look at first the stationary point. So, we take the first derivative d f by d x 1 and d f by d x 2 and get solutions for x 1 and x 2. So, x 1 and x 2 turn out to be minus 2 and 0. So, x, which is a stationary point, is minus 2, 0. There is only one solution here. So, this is how we obtain the stationary point, by equating the first derivatives to 0 with respect to each first derivatives with respect to each of the variables. Then we formulate the Hessian matrix. So, the Hessian matrix of f of x is the matrix of the second derivatives. So, d square f by d x 1 square, d square f by d x 1 d x 2, d square f by d x 2 d x 1 and d square f by d x 2 square. This has to be evaluated at the stationary point minus 2, 0. So, we evaluate the we evaluate the Hessian matrix at minus 2, 0. So, we will get the second order derivatives now. So, d f by d x 1 was minus 2 x 1 minus 4. So, we differentiate this again with respect to x 1, you get d square f by d x 1 square minus 2. We differentiate this with respect to x 2, you get a 0. Then d f by d x 2 is minus 2 x 2, you differentiate that again with respect to x 2, you get minus 2, and this will be same as d square f by d x 1 d x 2. So, we got all these values. We now formulate the Hessian matrix. Look at these values now. The second order derivatives are all constants here. That means, they are not functions of either x 1 or x 2. In general, however, they will be functions of x 1 and x 2, and therefore, you have to evaluate the Hessian matrix at the particular stationary point x 1 and x 2 by substituting the values of x 1 and x 2. The fact that these are independent of the values of x 1 and x 2 may lead to the conclusion that the Hessian matrix is positive definite or negative definite in the entire range of the function, entire range where the function is defined, and therefore, it may lead to, if it is positive definite, it may lead to a positive definite means it is minimum value, and therefore, it may lead to a convex function. If it is negative definite, it may lead to a concave function. So, we have the Hessian matrix minus 2, 0, 0, minus 2 starting with these derivatives here. We are substituting these values and you get h is equal to minus 2, 0, 0, minus 2. To examine whether this is a positive definite matrix or a negative definite matrix or neither, we evaluate the eigenvalues. So, to get the eigenvalues, you get determinant lambda I minus h is equal to 0. So, we write lambda I minus h, determinant of that, as lambda plus 2 here, 0 and 0 and lambda plus 2 again here, which gives the lambda values which are the eigenvalues as -2 and -2. So, lambda 1 is -2, lambda 2 is -2. That is, there are two roots of this, both the roots are -2. Because both the lambda values are negative, this Hessian matrix is a negative definite matrix. And further, because the lambda values are not dependent on the x 1 and x 2, it means that the lambda values remain negative for all the values of x 1 and x 2 over which the function has been defined. And therefore, the Hessian matrix is a negative definite matrix over the entire range of the function. This means that the local maximum that we get is also in fact the global maximum, and therefore, it is a concave function. The function is a concave function. I will just read out the whole thing now for completeness. Because both the eigenvalues are negative, first of all the matrix is negative definite, and therefore, the function has a local maximum because of negative definiteness. It corresponds to a maximum value. Always remember, when we are making decisions based on the derivatives, higher order derivatives, negative magnitude corresponds to a maximum value. Positive magnitude of the derivatives or the matrix, Hessian matrix corresponds to a minimum value. So, therefore, the local maximum occurs at -2, 0. Further, as the Hessian matrix does not depend on x 1 and x 2 and it is negative definite matrix, the function is strictly concave, and therefore, the local maximum is also the global maximum. If you had the Hessian matrix and therefore, the eigenvalues as functions of x 1 and x 2, the Hessian matrix would have been negative definite only at that particular stationary point, and therefore, you would have obtained only the local minimum. Because the eigenvalues are independent of the values x 1 and x 2, which means that over the entire range of the function, the eigenvalues will remain the same. In this particular case, lambda 1 is equal to -2, lambda 2 is equal to -2 will remain the same, and therefore, the function is a concave function, and therefore, the local maximum that you obtain is in fact the global maximum. Let us look at, for variety, one more example. F of x is equal to x 1 cube plus x 2 cube minus 3 x 1 minus 12 x 2 plus 20. So, this is a function of two variables. We get the stationary points first by taking the first derivative with respect to each of the variables. So, df by dx 1 is 3 x 1 square minus 3 is equal to 0, set it to 0, and you get x 1 is equal to plus minus 1, and df by dx 2 is equal to 3 x 2 square minus 12 is equal to 0. So, you get x 2 is equal to plus or minus 2, and therefore, you get 4 solutions. X is minus 1 minus 2, plus 1 plus 2, plus 1 minus 2, and minus 1 plus 2. So, these are the 4 solutions that you get. So, these are the stationary points, and at each of these stationary points, you have to examine whether the point whether this point corresponds to a maximum or a minimum or neither of them. To do that, we formulate the Hessian matrix, evaluate the Hessian matrix at each of these stationary points, and then examine for each of these stationary points whether the Hessian matrix is positive definite or negative definite or neither. So, let us go to the Hessian matrix now. So, the Hessian matrix, there are two variables here, therefore, d square f by dx 1 square, d square f dx 1 dx 2, d square f dx 2 dx 1 and so on. This has to be evaluated at the stationary point. So, we take one by one stationary point and then evaluate that. So, df by dx 1 is 3 x 1 square minus 3, and therefore, d square f by dx 1 square will be 6 x 1, d square f by dx 1 dx 2 is 0, and similarly you have df by dx2 is 3x square minus 12 and d square f by dx2 square is 6x2, and the second order derivative with respect to x2 and x1 is 0. So, the Hessian matrix is 6x1 here d square f by dx1 square, 6x1 and 0, 0 and 6x2. So, this determines the Hessian matrix. Unlike in the previous example, the Hessian matrix is now a function of x1 and x2, and therefore, you have to evaluate the Hessian matrix at each of the stationary points that you have obtained. You have obtained 4 stationary points now. So, for each of the stationary points, we will have to examine whether the Hessian matrix is a positive definite matrix or a negative definite matrix. So, we will evaluate this for different stationary points. Either you evaluate the Hessian matrix at each of the stationary points and then obtain the Lagrange multipliers. Obtain the eigenvalues. We will introduce the Lagrange multipliers presently in this course, which are also denoted by lambda, but the eigenvalues we determine based on the Hessian matrix and then substitute the values of x1 and x2. So, that is what we will do here. Eigenvalues we determine determinant of lambda I minus h, which is lambda minus 6 x1, 0, 0, lambda minus 6 x2, and this is set to 0. So, we set this to equal to 0. And we get the solution lambda minus 6 x1, lambda minus 6 x2 is equal to 0, which gives values of lambda 1 is equal to 6 x1 and lambda 2 is equal to 6 x2. So, the Hessian matrix at 1 comma 2 will give us lambda 1 of 6 and lambda 2 of 12, both of which are positive. So, at 1 comma 2 you have 2 lambda values, both of which are positive, and therefore, the Hessian matrix is a positive definite matrix at the stationary point 1 comma 2. So, it is positive definite at x is equal to 1 comma 2. Because Hessian matrix is positive definite, the point corresponds to a minimum value of the function, and the minimum value of the function we can determine by substituting x1 is equal to 1 and x2 is equal to 2 in the original function definition. So, in this you put x1 is equal to 1 and x2 is equal to 2, and that is what you get as the minimum value, local minimum. Hessian matrix being positive means that the stationary point is a minimum value, and the minimum value is obtained by substituting the values x1 is equal to 1 and x2 is equal to 2. So, this is what you get. Then we move to the next stationary point. We remember we have 4 stationary points now. So, we go to the next stationary point. We evaluate this at minus 1 minus 2, that is a Hessian matrix at minus 1 minus 2. So, the lambda values will be minus 6 and minus 12. So, at minus 1 minus 2 at the stationary point minus 1 minus 2, you get the lambda values as minus 6 minus 12, both of which are negative, and therefore, the Hessian matrix is a negative definite at the stationary point minus 1 minus 2. Because the Hessian matrix is negative definite, the point minus 1 minus 2 corresponds to a maximum value. So, all the eigenvalues of the Hessian matrix are negative. In this case, there are 2 eigenvalues, both of which are negative, and therefore, the Hessian matrix is negative definite, and negative definite means it is a maximum value, and we calculate the maximum value as 38 by substituting x1 is equal to minus 1 and x2 is equal to minus 2. Like this, we go to the next available values. So, we will exhaust minus 1 comma 2 and 1 comma minus 2. That means, x1 is equal to minus 1, x2 is equal to 2. Re-evaluate your eigenvalues. x 1 is equal to 1, x 2 is equal to minus 2, re-evaluate the eigenvalues and examine whether all the eigenvalues are negative, all the eigenvalues are positive, or some of them are positive and some of them are negative. So, in this case you get the eigenvalues as minus 6 and 12 for this stationary point and 6 and minus 12 for this stationary point, which means out of the two eigenvalues one is positive and one is negative in both the cases. And therefore, we will not be able to, therefore, the points stationary points of minus 1 comma 2 correspond neither to a local minimum nor to a local maximum. Similarly, the point 1 comma minus 2 corresponds neither to a local minimum nor to a local maximum. So, out of the 4 stationary points that we obtained in this example, we could identify one as a local minimum, one as a local maximum and the other two as neither local minimum nor local maximum. And in fact, from the Hessian matrix we also saw that the Hessian matrix and therefore, the corresponding eigenvalues are in fact functions of x 1 and x 2, and therefore, the function is neither a convex function nor a concave function, and therefore, it behaves differently at different stationary points. So, this is what we did in unconstrained optimization. We started with the single functions of single variables, then extended it on to functions of multiple variables, but we did not attach any constraints. These are by far the simplest of problems, and they are introduced typically as just a background necessary for further optimization. In almost cases of engineering optimization, we will have a set of constraints, set of conditions that we want to impose on the problem. For example, let us say you are minimizing the cost of a reservoir, cost of a dam. Then you need to the conditions on what are the functionalities that you would like to expect, because obviously, if you want to have a minimum cost, it can be a 0 cost if you do nothing is the solution, but you would like to achieve some functional performance of the particular structure, and therefore, you would like to put conditions that minimum we need to produce certain amount of hydropower, or you want to maintain a minimum flood control, or you want to maintain the mass balance from one time period to another time period and so on. So, all the physical conditions that the problem has to satisfy often come as constraints, and these constraints will have to be included in the mathematical formulation of the optimization, and we will be optimizing a function subject to several of these constraints. So, any engineering optimization problem is almost always, unless we have some means of removing the constraints, a generally stated optimization problem almost always contains constraints, and therefore, we should be talking about constrained optimization. So, we will now start talking about constrained optimization, where we are looking at optimal values of the functions subject to a set of constraints. So, let us see, we will start with the simplest of the constraints, namely the equality constraints, and then we will go to more generalized inequality constraints. So, in the constrained optimization, we have a function f of x of n variables, that is multiple variables x 1, x 2, x 3 etcetera x n, and then we are subjected to a set of constraints of the type g j of x less than or equal to 0, j is equal to 1, 2 etcetera m. So, there are n variables and there are m number of constraints. Let us say you have 4 variables and 3 constraints, 4 variables, 4 constraints, 4 variables, 10 constraints and so on. if the number of constraints m is larger than the number of variables n, then in general the problem is overdefined, and therefore, there will be no solution unless there are what are called as redundant constraints. What do we mean by redundant constraints? If you state one of the constraint and the other constraint is automatically satisfied by stating this particular constraint, then the other constraint becomes redundant. For example, let us say that you have a constraint of the type 2x1 plus 3x2 is less than or equal to 6. This is one of the constraint in two variables. Let us say I have another constraint 4x1 plus 6x2 is less than or equal to 12. That means, simply multiply this by 2. Then naturally, whenever this is satisfied, this is always satisfied. So, one of the constraints becomes redundant constraint. Similarly, let us say you have x1 is less than or equal to 5 as one of the constraints. Then elsewhere in the model or in the formulation, you may have some constraint of the type 3x1 is less than or equal to let us say 25. The moment you satisfy this constraint x1 is less than or equal to 5, automatically this constraint is satisfied, 3x1 is less than or equal to 25. So, in general, when you have redundant constraint, and therefore, this becomes redundant constraint. In general, whenever you have redundant constraints, it means that not enough thought has gone into the formulations of the constraints. The constraints are after all formed based on the physical understanding of the system, and therefore, you may tend to add constraints which are in fact functions of other constraints that you have already included in the problem. So, whenever you have m greater than n, that is the number of constraints higher than the number of variables, the problem is in general overdefined, and therefore, you should be alert to the situation where you have redundant constraints in this. So, you should be able to identify the redundant constraints and remove the redundant constraints. We will see these more when we look at large applications, large scale applications of multiple reservoir operations and so on, where generally we tend to introduce redundant constraints. So, this is the concept of redundant constraints. Now, so typically we will have m less than or equal to n. So, when you have m less than or equal to n, that means the number of variables is larger than the number of constraints, and that is a type of problems that we will be addressing now. This is a generally stated problem where we are looking at maximization or minimization of a function subject to g j of x. We are not at this stage putting any conditions on the nature of the function itself. So, f of x and g j of x can assume any type of functions. They may be linear, non-linear and so on. So, we are not saying that either f of x or g j of x must be linear functions. From this general optimization problem, we will start the discussion with the simpler version of this general statement, where we will consider all the constraints to be equality constraint. So, from g j of x less than or equal to 0, I will start with g j of x equal to 0. That is, some functions of the decision variables x1, x2, x3 etcetera, all these functions are equal to 0. So, we start with problems with equality constraints. So, we are starting with this function with equality constraint. How do we state that? Maximize or minimize f of x subject to g j of x is equal to 0, and this is for j is equal to 1 to m. And x is a vector x1, x2, xn. it has n variables and we have m number of constraints. Now, in this general problem, we will discuss two simple methods. One is direct substitution, another is the method of Lagrange multipliers. In the direct substitution, what we do is, let us say you have m number of constraints. Because they are all equality constraints, it is possible for you to express m number of variables in terms of the remaining n minus m number of variables. There are n number of variables, there are m constraints. So, you express using these m constraints, which are all equality constraints. Using these m constraints, you express m number of variables in terms of the remaining n minus m number of variables and substitute them, and therefore, you have taken care of the m conditions, m constraints, and then converted the original constraint problem into an unconstrained problem with n minus m number of variables. So, this is what we do in direct substitution. And direct substitution is almost always handy when you have less number of constraints in classroom type of examples, where you may have 2 variables, 1 constraint, 2 variables, 2 constraints, 3 variables, 2 constraints and so on. But in most practical situations, where you have to deal with large number of variables, large number of constraints and so on, the direct substitution and also the nature of the constraints themselves. They may be highly nonlinear constraints and so on. So, the substitution may not be always very handy, in which case we go with Lagrange multipliers, which I will introduce in the today's class. So, in the direct substitution method, we reduce the problem to an unconstrained problem by expressing m variables in terms of the remaining n minus m variables. You have m constraints and you use these m constraints to express the m variables in terms of the remaining n minus m variables. Remember, all these m constraints are in terms of all the n variables, and we use these m constraints to convert the problem into a unconstrained problem of n minus m variables. For example, you have 3 variables x 1, x 2, x 3. We have 2 constraints. Both of the constraints contain all the 3 variables in general. Then we may pick 2 of the variables, let us say x 2 and x 3, and solve these 2 constraints and express both x 2 and x 3 in terms of x 1, and that is what we do. So, 2 variables we express in terms of the n minus m variable, which is 3 minus 2 variables, which is 1 variable, and that is x 1, and then render the problem as unconstrained problem with only x 1 involved. And once it is rendered an unconstrained problem, we know how to solve this. We have just seen the unconstrained optimization method. So, we use the unconstrained optimization method to solve such a problem. So, this is what we do in direct substitution. I again repeat, direct substitution is good only as a classroom type of examples, where you have less number of variables, less number of constraints and so on, where you can easily solve and substitute for some variables in terms of the other variables. Constraint equation that we come across in practical problems are often nonlinear, and therefore, direct substitution also becomes quite involved and difficult. So, let us see one example. Let us say that you have a function f of x is equal to x 1 square plus x 2 square plus 4 x 1 x 2, subject to a single constraint x 1 plus x 2 minus 4 is equal to 0. Now, this is of the form g j of x is equal to 0. So, this is the equality constraint. We have an equality constraint. So, let us say that you want to substitute for one of the variables. There are 2 variables, 1 constraint. So, n is equal to 2, m is equal to 1. So, we express m number of variables, which is 1 number of variable, in terms of n minus m variables, which is 2 minus 1, which is 1. So, we express x 1 in terms of x 2, x 1 is equal to 4 minus x 2, and then substitute it in the original function. So, x 1 square, which is 4 minus x 2 square, plus x 2 square plus 4 x 1 4 minus x 2 into x 2. So, we have converted the original problem of 2 variables into a problem of 1 variable using the constraint. So, this becomes 16 plus 8 x 2 minus 2 x 2 square. So, this is a function of a single variable. Once we know, once we have converted the function into a function of single variable and then got rid of all the constraints, we can solve this problem as an unconstrained optimization problem, and in this particular case of a single variable. So, we take the first derivative df by dx2, the x 2 is the only variable here, and then equate it to 0, you get x 2 is equal to 2 as a stationary point. Go to the second derivative, that becomes minus 4, from here it becomes minus 4, which is negative, and therefore, the global maximum occurs. Actually, from here we conclude that it is a local maximum occurs at this location at x 2 is equal to 2. So, this is what we do in direct substitution. That is, we substituted for one of the variables in terms of the other variable, m number of we substitute for m number of variables in terms of the other n minus m variables, and then convert the problem into an unconstrained optimization problem in terms of n minus m variables, and we use the methods of unconstrained optimization and then solve the problem. However, for large problems, this method is not a elegant method, it will be quite cumbersome, and therefore, we evolve methods of Lagrange multipliers, which are much more rigorous, which is much more rigorous method of calculus. We have n number of variables, we have m number of constraints. In the direct substitution method, what we did is we eliminated a certain number of variables. In fact, we eliminated m number of variables. In the Lagrange multiplier method, we add m number of variables, which means we introduce an additional m number of variables. Let us see what we do in this. Corresponding to each of the constraints g j of x, we introduce a Lagrange multiplier. So, g 1 of x has lambda 1, g 2 of x has lambda 2, g 3 of x has lambda 3, etc. Associated with each of the equality constraint, we have a Lagrange multiplier. So, that is what we do, introduce one additional variable lambda j corresponding to each constraint j, which is g j of x is equal to 0 as our constraint. We associate with each constraint a Lagrange multiplier lambda j, and then we formulate the Lagrange function. You have the original function f of x, which is a function of n number of variables. We have the constraints g j of x is equal to 0. Associated with each of these constraints g j of x, we have now a Lagrange multiplier lambda j. We formulate what is called as a Lagrange function using the function f of x and the constraints g j of x along with the Lagrange multipliers lambda j. And the Lagrange function L is written as Lagrange function is written as L is equal to f of x, which is the original function, minus lambda j g j of x. So, you have g j of x here, there will be summation here. I am sorry, let me write. I will rewrite this here. L is equal to f of x minus summation j is equal to 1 to m, there are m constraints, lambda j g j of x. Now, this is how we formulate the Lagrange function, that is Lagrange associated with the original function f of x and the set of constraints g j of x with Lagrange multipliers. These lambda j's are called as the Lagrange multipliers. You have one Lagrange multiplier associated with one constraint. So, g1 of x will have lambda 1, g2 of x will have lambda 2 and so on. So, there are m number of Lagrange multipliers and this is the function L, Lagrange function. Now, because gj of x is equal to 0, what does that mean? Optimizing L also means that you are optimizing f of x. So, the problem is now transferred to unconstrained optimization problem. So, you are looking at only L is equal to f of x minus lambda j summation lambda j gj of x as the Lagrange function. So, we will work with this function now by converting the constraints using lambda j gj of x. So, we have incorporated all the constraints into the Lagrange function. So, we will work with Lagrange function. How many arguments are there in Lagrange function? You had n number of variables here x1, x2, x3 etc., xn. Then you have m number of multipliers lambda 1, lambda 2, lambda 3 and so on. So, when you are optimizing L, you have to the necessary condition is that you differentiate L with respect to each of its arguments. So, differentiate L with respect to x1, with respect to x2 etc., first order derivatives with respect to x1, x2, x3 etc., xn, also with respect to lambda 1, lambda 2 etc., lambda n and equate it to 0. So, this is what we start with as necessary condition. So, L is written in the longer form as f of x minus lambda 1 g 1 of x minus lambda 2 g 2 of x etc., minus lambda m g m of x. So, the problem of n variables with m constraints is now changed to a single problem of n plus m variables with no constraints. Just distinguish this with respect to what we did in the direct substitution method. In direct substitution method, you had m number of constraints, we expressed the m number of variables, which actually means we eliminated m number of variables and then expressed the original problem with n minus m number of variables, still making it unconstrained optimization. In the Lagrange multiplier method, on the other hand, we introduce m number of additional variables, which are called as the Lagrange multipliers, and therefore, the original problem of n variables with m constraints has now been converted into an unconstrained optimization with n plus m number of variables. We have added m number of variables in this case. So, the necessary condition, we formulated the Lagrange now. The necessary condition is, we state it formally, for a function f of x subject to the constraints g j of x is equal to 0, j is equal to 1 to m, to have a relative optimum, which means relative minimum or relative maximum at a point x star, this is a stationary point x star, is that the first partial derivatives of the Lagrange function with respect to each of its arguments must be 0. So, we have formulated the Lagrange here, L is equal to f of x minus summation j is equal to 1 to m lambda j g j of x with respect to each of its arguments, namely its arguments are x1, x2 etc., xn, lambda 1, lambda 2 etc., lambda m. First derivatives must be 0. So, dl by dxi is equal to 0 for I is equal to 1 to n, dl by d lambda j must be equal to 0 for j is equal to 1 to m. So, you formulate n plus m equations, there are n variables here, n equations here, there are m equations here. So, n plus m equations, solve them simultaneously, you will get solutions for these n plus m variables. What are the n plus m variables? x1, x2, x3 etc., xn, lambda 1, lambda 2, lambda 3 etc., lambda m. So, you solve for xi's as well as lambda j's, and that constitutes the stationary point. So, you get after solution of these n plus m equations, you get x star and lambda star as the solution. This is in fact called as the stationary point. Then we go to sufficiency condition. So, this is a necessary condition, that means the first order derivatives of the Lagrange with respect to each of the arguments must be equal to 0. From that you solve n plus m equations, you get x star, which is x 1 star, x 2 star, etcetera, x n star, lambda 1 star, lambda 2 star, etcetera, up to lambda j star, lambda m star. So, you get the solutions of that. Then we move to the sufficiency conditions. Sufficiency conditions are always in general in terms of the second order derivatives. Now, you have Lagrange function L, which is a function of x 1, x 2, etcetera, x n, and lambda 1, lambda 2, etcetera, lambda m, and you also have the constraints. You have m number of constraints, each of which is a function of n number of variables. So, we will see here, we will define L I j. This part you just be clear on the notation. We define L I j as the second derivative of the Lagrange L with respect to the two variables x I and x j. So, L I j is second derivative of the Lagrange L with respect to variable x I and x j evaluated at the stationary point x star lambda star. We denote by g I j the first order derivative of the jth constraint g j of x with respect to the variable I. So, d g j by d x I is what we denote as g I j. So, I is the ith variable, j is the jth constraint, and we are talking about the first order derivative. So, L I j corresponds to the second order derivative, g I j corresponds to the first order derivative, and this is done for j is equal to 1 to m for each of the values of I. So, you have L I j and you have g I j. I corresponds to the variable, j corresponds to the constraint in this particular case g I j here, and in this case it corresponds to the two variables x I and x j. So, just be clear about the notation that we are using. Then we formulate a determinant. So, you got the second order derivative with respect to each of the variables, and you got the first order derivative of the constraint with respect to each of the variables. Using these derivatives, now we formulate a determinant. This determinant is formulated as follows. We will not go into the theory of how the sufficiency condition is arrived at and so on. Those who are interested are referred to the classical book by S.S. Rao, that is Optimization Theory and Practice. But we will not worry about the theory, but we will see how the sufficiency conditions are formed for a given particular problem, and then how we arrive at the conclusion of whether the stationary point corresponds to a maximum or a minimum. We formulate this determinant thus. You have L I j defined here. So, L 11 minus z, L 12 etcetera L 1 n, which means with respect to first variable 1, 2, 3, 4 etcetera up to n. So, that is what we are taking L 11, L 12 etcetera L 1 n, and for the first term you are taking minus z. Similarly, L 21, L 22 minus z etcetera L 2 n, L n 1, n 2, n n minus z. So, these are n terms by n terms. This is what you formulate here, followed by G 11, G 21 etcetera G m 1, which means the first constraint with respect to first variable, second constraint with respect to first variable, mth constraint with respect to first variable, then G 12, G 22, G m 2, first constraint with respect to second variable, second constraint with respect to second variable, mth constraint with respect to second variable. Like this, you come to first constraint with respect to nth variable, second constraint with respect to nth variable, mth constraint with respect to nth variable. So, these are defined from here. So, these are the first order derivatives of these constraints with respect to the variables here. So, these are m terms and this is n terms here on along this. Then we come to the lower left part of the determinant. We take the transform of this and then we take the transpose of this part and then put the transpose of this part here. So, G11, G12 etcetera G1n we arrange them horizontally, G21, G22 etcetera G2n we arrange horizontally and Gm1, Gm2 etcetera you arrange horizontally. So, this is how we formulated the three parts of this determinant. There are remaining m by m terms here. This will be m and this is m. So, m by m terms, all of them you put it as 0. So, this is how we formulate the determinant D and set the determinant D to 0 equal to 0. There are only the unknowns are z here. Just for clarity, I will again explain how this determinant is formed. We have Lij d square L by dxi dxj. We know the function L. Take the second order derivative with respect to variables xi and xj, that defines Lij. For example, L21 will be second order derivative of L with respect to dx2 dx1. So, that is how you formulate Lij. L22 for example, will be d square L by dx square dx2 square. Then Gij you define as the differential of the jth constraint with respect to ith variable. So, you know Gij, jth constraint with respect to ith variable. Now, you come here, you write m terms G11, G21, Gm1, G12, G22, Gm2. Similarly, L11 minus Z, L12 minus Z, etcetera, and transpose this and put it in terms of G11, G12, etcetera, G1n. And the remaining m by m terms, you put it as 0. So, this determinant D, you set it to 0, you get a polynomial in Z. When you formulate this determinant and set it to 0, you get a polynomial in Z of the order n minus m. These are n plus m terms here, n plus m terms here, and only these n terms have Z. You get a polynomial of the order n minus m in Z. Solve for that, solve the polynomial for Z, you obtain Z values. So, it leads to a polynomial in Z of the order n minus m. We solve for Z. If all the Z values are positive, then the x star, which is the stationary point, corresponds to a local minimum. If all Z values are negative, x star corresponds to a local maximum. If some values are positive and some are negative, x star is neither a minimum nor a maximum. So, just quickly we will recapitulate what we did for in the Lagrange multipliers. We associate with respect to each of the constraints a Lagrange multiplier. Gj of x we associate with lambda j of x, lambda j we associate with each of the Gj of x, and therefore, we have as many Lagrange multipliers as we have number of constraints. Then formulate the Lagrange function L as f of x minus summation j is equal to 1 to m, you have m number of terms lambda j Gj. So, that is the Lagrange function. Then the necessary condition for that is that the first order derivative of the Lagrange with respect to each of the arguments must be equal to 0. What are the arguments? X1, X2, etcetera, Xn, which are the original variables, and lambda 1, lambda 2, lambda 3, etcetera, lambda m, which are the additional variables multipliers that we have added. So, you formulate n plus m equations like this. solve for the n plus m equations, you get the solutions for x1, x2, etcetera, xn, which defines x star, and lambda 1, lambda 2, lambda m, which defines lambda star. Now, this is a stationary point x star lambda star. Then we go to the second order derivative to get the sufficiency conditions. We get the second order derivative L I j, which is d square L by dxi dxj. That is the second order derivative of the Lagrange function with respect to the variables xi and xj. Similarly, we get gij, which is the first order derivative of the jth constraint gj with respect to the ith variable xi. Then we formulate that determinant and introduce this is the determinant that we formulate, and then introduce z in the diagonal elements of L I j only, and then solve for z. This determinant, when you set it to 0, it gives a polynomial of the order of n minus m and solve for z. If all the z values are positive, then the stationary point x star corresponds to a minimum. If all z values are negative, then it corresponds to a maximum. If some of them are positive, some of them are negative, then it corresponds to neither a minimum nor a maximum. So, we will solve some numerical examples in the next class on Lagrange multipliers. Remember, Lagrange multipliers is the most powerful method, and in fact, the physical significance of Lagrange multipliers etcetera we will be using subsequently when we deal with sensitivity analysis in the linear programming and so on. So, understand the Lagrange multiplier method correctly, and we will also see the interpretation of the Lagrange multipliers. So, in today's class quickly we just started off with the unconstrained optimization problems, 2 examples we solved, and then went on to introduce the constrained optimization problems. And in the constrained optimization problems, we have started with problems with equality constraints. An easy way of handling the equality constraints in simple problems is by direct substitution, where you can replace m variables by expressing them in terms of the remaining n minus m variables and rendering the problem to be an unconstrained optimization problem. In the more rigorous Lagrange multiplier method, we add m number of variables. In fact, we add m number of Lagrange multipliers, one associated with each of the constraints. You have m constraints, you add one Lagrange multiplier associated with each of the constraints, and then we formulate the necessary conditions and the sufficiency conditions. We will continue the discussion on the Lagrange multipliers in the next class. In fact, we solve some numerical examples, so that all points are clear on the Lagrange multipliers. Thank you for your attention.